in phase and the quadrature phase signals that we are going to have it. And we have seen that the in phase signal product is going to be our m of t, and quadrature product that we are going to have it is of the Hilbert transform of m of t. Accordingly, I have seen generate SSB signal by the phase method or that of the frequency discrimination method. And seen for the frequency discrimination method, back the original signal that we are having. So in both these cases of ISC or SSB signal that we are going to have it without any carrier, we are seen that require a carrier at the receiving end to demodulate or detect the required baseband signal. Suppose if you don't have a coherent carrier generate, let us look into the DSS a signal that we are going to have it. What is the signal for this DSBSC? Your S of t is, so to get back your signal, output of again a product modulator, we are going to have m of t cos omega ct into cos omega ct plus phi. If you say that a phase variation is going to be occurring, if phi is 0, then we are now the output is 1 by 2 AC m of t. So that by passing through your low filter, the second harmonic of that cos omega ct will be eliminated, and we are going to get back our required baseband signal. But when phi is not equal to 0, what will happen? Output of the low pass filter because V naught of t required baseband signal. But phi is not 0, then we are having a transmitted signal that is generated, or a carrier generated transmitter and a carrier generated at receiver. Two generators we are having, one at the transmitter and one at the receiver. Therefore, even though you say that you have designed a circuit to have the same frequency and phase, but as the time varies, your phase is going to vary. There phi is a variable instead of that we are going to have. Phi is varying. What is the value of cos phi? It is going to increase or decrease. Therefore, your output is going to be increasing or decrease or max. If you say that you have your V of t with a variation in the frequency, with a frequency variation of delta omega. Instead of omega c, the frequency that we are generating at the receiver is omega c plus delta omega. Ah, frequency is f star that means you have a spectrum like this, your baseband signal with FM and minus FM. Omega positive or negative, that we are going to have it. Therefore, we have two that we are going to have it, so that our ear can see that and then get you the signal that we are going to have it with this delta omega being 30 hertz that we are going to have it. Therefore, this is what the importance of the carrier that we are going to have it in case of SSB signal. But suppose you have sin omega CT. This is the transmitted signal that we are going to have. So this we are multiplying with signal CT what is the output you are going to get after the low pass filter. This cos omega CT we can write it as cos A P. So cos omega CT in cos phi that we are going to have it. Therefore, we can write cos A into cos B we are getting here minus spectrum that we are going to have it. Then we are going to have this of M of f exponential plus j theta for f have it. Therefore, we have to see that this phi is minimum that we are going to have it. Similarly, for different frequency, I do L plus B and delta f is positive, or it. So this is the signal that we require, where m of f because of this frequency variation that we are going to have it in the carrier that we are, and for LSB delta f is negative. The spectrum is moving, frequencies also will be overlapping, and your detection will be a problem. Therefore, we should have this data also to be very stable carrier that to generate our receiver. Say that we have to variation to be as much low as possible. As you said, this delta f should be less than your signal, the required phase, and the frequency of the received signal that we are going to have. We reduce to a certain extent the generation of the area should be very stable. Both your SSB and SSB, we said that not sending the carrier, but the last modeling, the receive signal, if you have carrier or the carrier at the receiver, then you will be having m of t into cos omega ct. Let us say that this we have added of detector. Will it be giving you the required output or not? So what is this will be equal to expand this into cos a cos b of t plus ac cos phi. For this we can write it as of t cos omega c plus theta. Cos phi plus m of t square plus ac sin phi m of t into ac into 1 plus 2 is larger than your m of t. This will be eliminated and it will be eliminated by passing through a capacitor. So that what is the output you are going to get? This is the same as your coherent detection with a phase variation. So by adding your carrier, we are going to get the same signal that we are going to have it as that of your coherent detection that we are going to have it by using a simple LF detection. One thing is your M of t should be having less amplitude compared to your carrier that we are going to have it, and this carrier what we are having is generated over receiver, so you can have the required amplitude or the power that we are going to have it. Therefore, you can go for original signal of your coherent detection that we are going to have it. So similarly, you can derive for your SSB signal also. States that the same variation you are going to get as that of your coherent detection of your SSB SC signal that we are going to have it. So like this, you can have a variation in the detection process that we are going to have it, so that you will be going for the coherent detection or envelope detection if you have a pilot carrier that we are going to have it. So these are the different ways of detecting the SSB signal or the DSC signal that we are going to have it. So far we have seen the different amplitude modulation techniques that we are going to have it. So we have seen amplitude modulation, which are saying that a double sideband with carrier. Then we have a double sideband with suppressor carrier. Then we have an SSB signal that we are going to have it. So these are the three variations that we have seen so far. So what is the comparison between these different modulations that we are going to have it? So we are having ASM, that is DSP with carrier, DSP suppressor carrier, and SSB also the suppressor carrier. So what will be the comparison that we are going to have it? What is the power requirements for our different modulations? So this is going to be 1, we require only 33% here, and this is around 17% only. That means for the AM transmission we require higher power transmitters to have same efficiency. If you say that this is going to be 1 kilowatt, you are going to transmit, this is 330 watts, you can have it, and this is half of that. So this much power is enough to transmit. Therefore, the transmitter cost of your system in the case of SSB is much less compared to that of your AM transmitter. But what about the bandwidth? We require here 2 FM and whereas in SSB we require a bandwidth of only FM. So when the bandwidth wise there is no advantage between your AM and DSBSC, whereas FM, the SSB, we are going to get half that of the bandwidth that we require for either AM or DSBSC signal that we are going to have it. So we are saying that this requires more transmitted power to have the same efficiency, whereas this is requiring less transmitted power to have the same information content that we are going to have at the receiver. But what is the disadvantage? in the case of SSB or DSB. The disadvantage in the case of DSB or SSB compared to your AM. Carrier. So we are using here for DSB-SC and SSB-SC a coherent carrier. That means in the case of AM, the detection is a simple rectifier detector or envelope detector. A simple diode and resistor capacitor combination is enough to identify the envelope if the modulation index is less than 100%. So we are able to obtain the envelope by going for a simple envelope for this AM. But whereas for SSB and DSB, we require a coherent carrier. That means complex circuits you have to use at the receiver, whereas here we require more power to be transmitted. Whereas receiver circuit of AM transmission is very, very simple compared to that of your DSB-SC or SSB transmission that we are going to have it. And one more variation that we can observe is with DSB or SSB, we cannot generate very, very high powers. Whereas with the AM, we can generate high powers that we are going to have it. Some advantages here and some advantages in SSB. So here we are saying that the receiver circuit is very, very simple. Therefore, we will be using AM for our radio broadcasting or general communication that we are going to have it. Because receiver circuit, we have only one transmitter, one radio station and thousands of receivers. Therefore, the home receiver should be very simple and less cost. That's why for radio occasion, we will be using amplitude modulation, point-to-point communication. Point-to-point communication, we will be going for SSB signal that we are going to have it. Signal transmission. What do you mean by point-to-point? You have one transmitter and one receiver, or a fewer number of receivers, not like that of your radio receivers. Every home will be having number of receivers. Therefore, for SSB we will be going for point-to-point communication, and AM will be going for radio communication. And here, in the case of this modulation, we will be having an effect what you call fading. What do you mean by fading? Fading, change in phase. A general term that we can have it is fading is decreasing in the level of the signal that we are going to have it. You have a good picture, it is faded out. What does it mean? You are not able to completely visualize the picture. Similarly, signal also, it faded. That means the signal is not completely audible or to be recorded. So it is having a lesser values that we are going to have it, or variations in the signal that we are going to have it. So we are having one transmitter, a receiver here. So the signal may be received at this point by number of paths that we are going to have it, depending on different propagations, your ionospheric propagation, ground wave propagation, and so on, which you are going to study in your transmission lines. So we are having different propagations and all these things will be coming here at your receiver, and as you look into this, the distances that the signal travels is of different lengths. That means the time it takes is going to be changing. So when the time changes, the signal frequency is not going to change, but the phase is going to change. Therefore, the signal, the total effect of the signal that we are going to have it at the receiver will be increasing or decreasing, and sometimes it will be zero also, because all the phases that we are going to have it to add these things, the signal will be zero. That means even though the transmission is there, you are not receiving the signal. So this we call it as the fading of the signal, because of different paths the signal takes to reach the receiver. And another one that we are going to have it is selective fading. We have fading, and we are calling this as selective fading. As we are seeing that the time it takes for the different frequencies, it is going to be of different phase variations that we are going to have it. So some frequencies may be attenuated completely, and some frequencies may be received at your receiver. So only certain frequencies are lost and certain signals are received. That means again you are having some distortion, because unless you get all the frequency components of the signal, you will not be able to recover back the original transmitted signal. Therefore, we have to look into this fading and selective fading also. In the case of these amplitude modulation techniques, we are going to have this fading, and out of this, SSB gives you lesser fading effect compared to your TSB or AM transmission that we are going to have it. But because here in SSB we have only one sideband, whereas in DSB we are having two sidebands, right? FC minus FM and FC plus FM. So two frequencies. So the phase variations of these two frequencies, as they are saying that the selective fading is more effective in the case of DSB compared to that of your SSB signal. Therefore, the fading effect is going to be less in the case of SSB compared to that of your DSB and amplitude modulation that we are going to have it. In addition to this, so these are different comparisons that we are going to have it for different modulation techniques that we have seen so far. There were AM, DSB, and SSB. And all these modulations, we call it as linear modulation. We are giving a carrier frequency cos omega ct, and we are modulating this by cos omega mt. Will the output frequency, depending on the frequency components of the input or amplitudes of your input, not on the amplitudes of your AM or AC. But one thing is, the amplitude of this frequency or this frequency will be depending on this AC and AM, but not the frequency components. And also we have seen that if we have FC1 and FC2, FM1 and FM2, two tone frequencies that we are going to have it. If you have only FC1, how many frequencies you are going to get in output spectrum? How many frequencies you are getting? FC plus FM1 and FC plus FM2. Two spectral lines. Whereas if you have two frequency components in the baseband signal, we are getting four spectral lines. Similarly, if you have four in the input baseband signal, we are going to get 8 spectral lines. Therefore, we are having a linear combination between the input number of spectral lines in the baseband signal to that of your output spectral lines that we are going to have. So we are having a linear combination in this one. That's why I call this as a linear modulation. But that doesn't mean that suppose you are having cos omega m1 of t, and this gives you an output s1 of t, and you have cos omega m2 of t. This gives s2 of t. When you have these two, m1 of t and m2 of t, this is m1 of t baseband signal, this is m2 of t. So m1 of t gives you s1 of t and m2 of t gives you s2 of t. But your m1 of t plus s2 of t, which gives you s of t, may not be exactly equal to this s1 of t into s2 of t. But because the spectral lines we are having a linear variation that we are going to have it, this we call it as a linear modulation techniques that we are going to have. All your amplitude modulation techniques, we call it as a linear modulation technique. So this is about the comparison between the different AM modulation techniques and how they are affecting on the noise or your fading. So that with two-stage generation, we'll be able to get the required sideband without the unwanted sideband, either LSB or ESB. But suppose you have a signal like this, to get only one sideband, you require very, very sharp cutoff filters, which will not be possible. Whereas, if you have designed a circuit like this, the lower sideband and part of the other sideband, or upper sideband and part of the other sideband. So designing this filter is going to be easy to compare to having a sharp cutoff to generate your SSB signal. Whereas if this is FM, this is FC minus FP. Therefore, the bandwidth that we are going to have it is FM plus FP. The west is part of the frequency that we are going to have it. So additional portion we are going to have it. This we are saying that is the vestige part of your unwanted sideband. That's why we call this as vestigial sideband modulation. That is VSB. In the case of your TV signal, you will be having a DC component also. That means we are going to have a spectrum starting at 0 and going up to the high frequency. Not only this, the TV signal will be having a highest frequency of 5 megahertz for CCRP standards. So 0 to 5 megahertz we are going to have all the frequency components in your video signal. So if you use amplitude modulation, what is the bandwidth that we require? The bandwidth that we require to transmit a TV signal twice that of the highest frequency. Therefore, we require here 10 megahertz. So for each channel signal, we require 10 megahertz. Whereas by going for this vestigial sideband modulation, we are going to reduce this to 7 megahertz. So our CCRP standards will be allowing only that of 7 megahertz instead of 10 megahertz. So 3 megahertz reduction or the saving we are going to have it in the bandwidth of each channel that we are going to have it. So we require to reduce the bandwidth so that the bandwidth is limited and not producible by any other means. Therefore, we have to utilize it properly by reducing the bandwidth, and that's why I am going for a vestigial sideband modulation of the signal so that the limitations of your SSB filter design can be eliminated here. So what is this signal that we are going to generate and how it will look like? So we are having your M of t. This you pass through a product modulator. So what is that we are getting here? A DSBSC signal. This we are passing through a filter with the response h of f, so that we are getting a VSB signal. We'll see what should be h of f. So this is a simple generation of your VSB signal, provided you have the required filter here. And how to generate this filter, or what should be the characteristics of this filter, and what is that we require after transmitting at the receiving end, we have to get back our signal M of t, right? Therefore, if you give this S of t at the input, at the receiver, to another product modulator with some AC prime cos omega ct, a cause and detection we are going to have it. Then have a low pass filter. This should give rise to your M of t. So with this restriction, we want to find out what is going to be our h of f that we are going to have it. So we are having the signal here, and which are saying that when you have this S of t multiplied with this cos omega ct, What is the spectrum of this? Suppose if you say that this is V of t. V of t is S of t into AC prime cos omega ct. Therefore, what will be V of f? S of 1 by 2 AC prime, the S of f minus fc plus S of f plus fc. Okay, because they are having a product modulation here. But what is S of f? This is the spectrum of this. And what is S of t? The part of these two with a filter that we are going to have it. Therefore, our S of f will be equal to 1 by 2 AC m f minus fc plus m f plus fc into h of f, because this is cascading. So this is the spectrum of the transmitted signal S of f, whereas the output that we are going to have it before the low pass filter is this. Therefore, what will be our V of f? This V of f will be equal to 1 by 2 AC and the shifted version of this S of f. What will be? So this we want to shift by minus fc. So when you have this, this is going to give you f minus 2fc, whereas this will be giving you m of f only, f minus fc plus fc. So this gives you m of f and this gives you m of f minus 2fc. Therefore, this I will take it as m of f. Okay, even this. So for this one, this gives you m of f, and for this one, when f is equal to f plus fc minus fc, this gives you m of f. And what is this? H of f minus fc and h of f plus fc. Therefore, this is m of f into h of I am taking out this for f equal to f plus fc. So h of f plus fc into m of f. And for this one, we are getting f minus fc. So h of f minus fc. So m of f plus, as I seen that this gives you s of f minus 2fc, right? So therefore, this is m of f minus 2fc into h of f minus fc plus m of f plus 2fc into h of f plus fc. Other two terms. Therefore, when you have This is your baseband signal, M of f. What is that V of f? V of f will be with reduced amplitude 1 by 4 AC prime, and this is Fc, and this is 2Fc, and minus Fc, and minus 2Fc. So this is, suppose if you say that you have a upper side band, a VSB signal at 2Fc. This S of f is VSB signal at Fc, whereas V of f is giving you the VSB signal at 2Fc and M of f at the baseband signal. Therefore, if you pass this to a low pass filter, that's what we are doing here. What is happening? This will be eliminated. Only you are getting your M of f. That means after low pass filter, this will be eliminated and we are getting V naught of f. So this is V naught of t, which you are making equal to M of t. When this will be equal to M of t proportional to M of t, if this is a constant, 1 by 2 AC prime M of f into some other constant. If it is a variable with frequency, then we are not getting our required M of t. Whereas by going for this, so if you say that H of equal to 2 H of Fc, where this H of Fc is some constant, that is spectrum at center frequency Fc, and this is constant. Therefore, when this is constant, this is nothing but your M of f into some coefficient, a fixed coefficient. So inverse of that is your M of t only. So we are having the output is some k times M of t. So are we getting the signal or not? Provided this is a constant. That means your filter characteristics should be such that H of f minus Fc plus H of f plus Fc should be equal to a constant. So typical characteristics of this, and this is 1. So from the center frequency, if you move here and if you move at the same time, if you add these two, the value equal to 1, right? This value plus this value, you add Fc plus some value or Fc minus some value. You are getting the required constant that we are going to have it. So if you can design your network or your filter having this type of frequency characteristics, then we can generate the VSB signal. This is what your VSB signal. So that we are giving again to a product modulator and low pass filter. We are getting your required baseband signal that we are going to have. Therefore, this is what a basic principle of getting you the VSB signal in spectral domain. So far we have seen all the cases, the spectrum, how it moves and what variations you are going to get and so on. In the case of SSB, we have got a time domain representation also, taking the in phase and quadrature phase signals that we are going to have it. Therefore, your S of t, we can write as some SC of t into cos omega ct minus SS of t into sin omega ct. The in phase and quadrature phase signals that we are going to have it. So this is the time domain representation. So what will be our SC of t or SS of t that we are going to have it? So if you multiply this, S of t with some omega ct, or this in the spectral domain S of f minus fc plus S of f plus fc. And this gives you for this one as 1 by 2 AC m of f. Similar lines of that of the SSB, are not putting all the steps here. Okay, put in between steps and show that this is the spectrum that we are going to have it. So this gives you of AC m of t. Whereas if you multiply this with AC sin omega ct, so we are going to have this along with this filter characteristics also. Therefore, the filter characteristics that we are going to have it will be coming here. Have it. Or multiplying this with this one and considering this h of f, we are going to get the characteristics as like this. This is your minus fe and this is plus fe. Where you want the prestige part, how much f of e that you want, you are to design. So if you pass your m of t to a filter having these characteristics, we are going to get this quadrature phase signal that we are going to have it. This are represented as ms of t. How to get ms of t? Passing this m of t to a filter like this, or a system like this having the characteristics between minus fe and plus fe. The linear variation that we are going to have it. Because what we are doing is, even though we say that we are having a vestige part of your what we are doing is, so we are losing some part here that will be equal to this part. So the total energy that we are going to have it is as that part of your SSB signal only. So some part of this we are removing. and we are adding some part of this. That's what we are doing here. Adding and subtracting the required part that we are going to have it. So that you reduce some part of the wanted sideband and some part of the unwanted sideband or the vestige part. So this we are giving as the input. We are going to get the in phase, the quadrature phase signal ms of t that we are going to have it. Therefore, the required signal to be generated is m of t cos omega ct minus ms of t sin omega ct. So this is what the time domain representation of your VSB signal. So how to generate the VSB signal? So you can draw the block diagram. Will be equal to AC sin omega ct. Use this to another product modulator. And what should be input? Another input for this? ms of t into sin omega ct. So you have a filter here as a network. We are giving input m of t and we are getting output ms of t with these characteristics. We are going to the product modulator. That means the second pair getting. So we have to subtract one from the other. So therefore this is minus and this is plus. This is your and what is the sideband we are transmitting here? The upper sideband and a part of lower sideband because we are having a minus here. If we have a plus, then we are going to get with lower sideband, the one that we are going to. Okay, so plus and minus or minus and plus that we are going to have it to give you the required VSB signal that we are going to. So this is what the generation of your VSB signal. Right? What is the difference that we are looking into compared to that of your SSB phase discrimination method of generation? Phase discrimination from this, what is the variation? Instead of having here this type of characteristics, this network is a Hilbert transformer. So that if you have this m hat of t, m of t minus m hat of t sin omega ct, that gives you your SSB signal. That means instead of this network, if you have a Hilbert transformer, you are getting SSB signal. For minus upper sideband, for plus you are having the lower sideband. So block schematics are the same except this block, the network that we are going to have it to generate this type of frequency characteristics that we are going to have it. So this is how we are generating our VSB signal that we are going to have. So in the case of the normal transmission of our TV signal, VSB. Say that this picture signal will be falling to 0 before the application of the sound signal, and this sound signal will be having a total bandwidth of 200 megahertz. For the AM transmission, the bandwidth that we require for each station is going to be 10 kilohertz. AM broadcasting, we require 10 kilohertz. Whereas for FM, each station bandwidth, we fix it as 200 kilohertz along with the guard band and so on. The total band, we are going to have it divided into each of these 200 megahertz band pass signals. Anyhow, we will see that when we are talking about FM modulators and the transmitters. So we are having this 0.75. So this is a typical ESP signal that we are going to have it of a TV signal. Our CCIR B standard with frequencies from minus so that total bandwidth is 10 megahertz. Right, in between we are going to have all the variations of your signal frequencies that we are going to have. So instead of 10 megahertz of your AM modulated signal, we are saving 30% of the bandwidth that we are going to have it. If you use AM, then we require 10 megahertz, whereas with VSB, we are having only 7 megahertz. So the picture modulation or AM, whereas your sound will going for frequency modulation. You have only the sound is of your 10 kilohertz baseband signal of 3 kilohertz that we are going to have it, that you modulate it and put your frequency modulation to require deviation so that the total band will be of 150 megahertz that we are going to have, so that we getting the required. This is 200 kilohertz bandwidth of, whereas your FM band starts with 88 megahertz to 108 megahertz. This is the FM frequency band for any transmission of frequency modulated signal that we are going to have it, and each station is going to be having 200 kilohertz, whereas AM is only 10 kilohertz that we are going to have. Anyhow, we'll see that why we require this much bandwidth when we are talking about the angle modulation or the frequency modulation that we are going to have. Here we are transmitting this VSB with that of receivers. Different points we have the receiver. That means your receiver circuit should be simple. Therefore, here by going for this VSB, we are going to have a envelope detector that we are going to have it, because we are having this also for both sound and the picture carrier signals that we are going to have it. And for your TV, we require this carrier also, because we have to transmit a high power signals that we are going to have it to transmit for the longer distances. Okay. Anyhow, this is of line of sight, and the maximum distance that we can cover is normally when you have it tower, this will be 70 to 100 kilometers that we are going to have it. a maximum area that you can cover. Within that radius, your TV signal will be transmitted. So we are going to have the number of receivers. So how to get back your original signal? By having an envelope detector. What is that signal that we are having? The S of t that I are going to have it is m of t omega ct. So the received signal R of t will be this m of t cos omega ct minus ms of t sin omega ct plus mka ac cos omega ct plus 5 carrier along with a ac sin into sin omega ct. Therefore, when Ka is sensitivity that we are going to have it, modulation sensitivity or percentage modulation, if this is larger, then you will be getting only the required baseband signal as the envelope detection output that we are going to have. The same derivation that we have done with the case of SSB, we have instead of m hat of t, we have ms of t. Meaning all the steps follows the same way, and we are going to get with envelope detector, we are able to get back the original signal m of t which has been transmitted. So this is how we'll be getting the simple detection of your VSB signal that we are going to have. So this will be about the vestigial sideband modulation, and I've already seen that of the AM, DSPSC, and SSB. We'll be completing the second unit also, right? Anyhow, we are much ahead of the system that we are going to have it, and if other people who are listening is not able to get the signal, they can send the feedback so that sometimes we'll be reviewing again what are all the topics that the people are never able to reach the inputs at the receiving points of the different colleges. Let the mentors or the students give the feedback so that some of the points can be reviewed again so that the doubts can be clarified. Explain again the various points that we have discussed so far. So next class we will be talking about the angle modulation. Okay, right? So go through the theory part and work out different problems on this. Yes, your AM signal or DSP signal or SSB. And after demodulation, how we are going to get back? So sometimes we will be asked to plot these spectral representations after modulation, and after detection before low pass filter, and how we are going to get the output. So the entire spectrum representation may be given instead of all the explanation that we are going to have it. So you have to explain that. So work out different problems on this. Similarly, on the power relations of your amplitude modulation. So work out different problems on these power relations that we are going to have it. And similarly,